Hi students, welcome to chapter 7, our solar system. In this chapter, we will talk about the classification of the solar system into inner planets and outer planets. We'll also talk about the similarities in the different planets and also the differences in the inner planets and the outer planets. So the main things covered in this chapter will be the important differences between the two broad categories of planets, which are generally called inner planets and outer planets, or more technically, terrestrial and Jovian. The similarities and differences among the large planetary satellites, including Earth's moon, how the spectrum of sunlight reflected from a planet reveals the composition of its atmosphere and surface, why some planets have atmospheres and why others do not. What is it that determines whether a planet will have atmosphere or not? We'll talk about the categories of many small bodies that also orbit the sun, such as asteroids and comets, how craters on a planet or satellite reveal the age of its surface, why a planet's magnetic field indicates a fluid interior in motion, and how diversity of the solar system is a result of its origin and evolution. First, let's look at the overall structure of the solar system. Here are the orbits of the 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. As you can see, Mercury, Venus, Earth, Mars are all located within this very small circle, which is the orbit of Mars. And then the outer planets are located at much larger distances. That's why they are called outer planets. Something to notice is that the orbits are almost circular. To the untrained eye, when we look at these look almost like perfect circles, but in reality, these are ellipses with very small eccentricities, as we have talked about in an earlier chapter. The other important thing to notice is that all these orbits are almost in the same plane, so that when we look from the side, this whole thing looks like a disk. And that is very important, and that has something to do with how the solar system was formed. Let's look at some of the data for the inner or the terrestrial planets. Here I'll point out only about some of the very important things. Some of these numbers here are in comparison with the Earth. For example, average distance from the sun in astronomical units. If you think about it, the astronomical unit is set because of the average distance of Earth from the sun, and therefore the average distance of Earth from the sun is 1. And so all these other distances expressed in AU are really in relative to the Earth's distance. Anyway, in AU, the Mercury's distance is 0.387 astronomical units. Venus is 0.723 astronomical units, and Mars is at 1.524 astronomical units. Orbital period in years, Mercury is 0.241. That is almost like a quarter. And so a quarter year, or about 3 months. Venus is about 0.6 years, which is about 7 months. Earth is, of course, 12 months or 1 year, and then Mars is 1.88 years. Orbital eccentricity. How much does the shape of the circle deviate from being a circle, and how much is it elongated? In terms of that, Mercury has the most eccentricity of 0.206. All others are very small. For example, Venus has an eccentricity of 0.007, Earth is 0.017, Mars is 0.093. However, because Mercury's orbit is so small, that eccentricity is less obvious. Inclination to the ecliptic, how much is the orbital plane of the planet tilted with respect to the Earth's orbital plane? In that also, Mercury has a high number of 7 degrees, but again, because of having a small orbit, it is not as apparent. Venus is tilted at 3.39 degrees. Earth has 0.00 degrees because that is the reference plane from which all the other angles are measured. Mars has an angle of 1.85 degrees. Now here is something especially important. The equatorial diameter, with taking the reference of the Earth as Earth's diameter as 1. So within the inner planets, Earth is the biggest planet. Mercury, Venus, and Mars all are smaller than the Earth. Mercury is obviously the smallest planet. Its diameter is 0.383 times that of Earth, or in other words, we can say about 38% that of Earth. Venus's diameter is about 95% that of Earth. Venus is also called a twin of Earth because it has properties very close or similar to Earth. Earth will obviously be 1. Mars is 53%. So the diameter of Mars is about half that of Earth. Then let's look at mass. Again, we'll skip the actual mass in kilograms and we'll look at the relative mass with the reference with Earth being measured as 1. So the relative mass. Here something is important to know, that when we see that the Mercury's diameter is 38% that of Earth, it doesn't look like Mercury is that small. But because of how geometry works, this is a one-dimensional measurement. And when we talk about volume, this becomes 3-dimensional. So the effect becomes much bigger. The volume of Mercury is much, much smaller compared to the volume of the Earth. And because of the smaller volume, its overall mass is also much, much smaller, much more smaller than just being 38%. So because of that, the mass of Mercury is 0.055. That is like 5% that of the mass of the Earth. Venus's mass is 81% that of Earth, and Mars's mass is 10% that of Earth. This effect is combined due to 2 reasons. One is, as I described, the relation between the 1 dimensions and 3 dimensions, but also the density of the material from which these planets are made. And if you will look at the last column here, last row, which compares the densities of the different planets, you will see that Earth is made from material which has the highest average density of 5515. And the other densities are similar. Mercury has 5430, Venus is 5243. But Mars is especially made of less dense material. Here is a picture that actually shows the relative sizes of planets with respect to each other. And a more realistic description of how far they are from the sun. So here I would like to point out that the inner planets are compared within themselves. So their sizes are realistic when compared to each other. And then outer planets or Jovian planets or gas giants are compared within themselves. So their relative sizes are accurate when compared to each other. However, we cannot compare the sizes of inner planets and outer planets because, as you can see, there's a scale. There's a scale of 10,000 kilometers next to the inner planets. And then there is a scale of 50,000 kilometers, which is 5 times as big, but still in the map here, in this drawing for gas giants, that is a smaller size than 10,000 kilometers. So just to give you an idea, the diameter of Jupiter is about 11 times that of the Earth's diameter. Comparing the volumes, about 121 Earths can fit inside Jupiter. Something else to notice, the distances of the outer planets from the sun. If we round off those numbers come out to be very nice whole numbers, which are easy to remember. For example, the distances of Jupiter, Saturn, Uranus, and Neptune are 5, 10, 20, and 30. Now, same numbers for the outer or Jovian planets. There's a third name for them, gas giants, obviously because they are giants and they are not solid like the inner planets. They are made up of gas. Okay, so because of that, one thing that will be very obvious will be, or noticeably different will be the density. So let's just jump to the last row here and look at the density. For the inner planets, we had seen that the densities were in the range of 4,000, 5,000. However, the average densities of Jupiter, Saturn, Uranus, and Neptune are 1,326, 687, 1,318, and 1,638. So except Saturn, the densities of the other 3 planets are somewhat comparable to each other, but Saturn is especially light. It is so light that it is lighter than water, less than water. Water has a density of 1,000 kg per cubic meter, and Saturn is 687. So here is an interesting thought experiment. If we had a large enough ocean of water in which we could try to submerge Saturn, Saturn would not go down, it would actually float in water. Let's look at some other numbers. Orbital periods, as we learned about the Kepler's third law, the bigger the orbit, the longer time the planet takes to go around the sun. And so that is shown here. Progressively, the orbital periods get bigger and bigger. Jupiter, 11.86 years. Saturn, almost 30 years. Uranus, 84 years. Neptune, 165 years. Orbital eccentricities, all of them quite small. Nothing to note. Inclination of orbit to the ecliptic, also very small, hardly noticeable. Equatorial diameters compared to Earth, that is interesting. Like I had mentioned, the Jupiter has an equatorial diameter of about 11.2 Earth diameters. Saturn is 9.5 Earth diameters. Within the outer planets, Uranus and Neptune are significantly smaller than Jupiter and Saturn. So Uranus's diameter is about 4 Earth diameters. Neptune is about similarly close. Let's compare the masses. The mass of Jupiter is 317 Earth masses. Saturn is 95 Earth masses. Uranus is 14.5 Earth masses, and Neptune is 17 Earth masses. Here's another picture with all the planets drawn right next to each other. Here, their sizes are accurate relative to each other, although their distances are not, but their sizes are accurate relative to each other. And in that picture, if you just look at Mars and Jupiter right next to each other, you can see how hugely different their sizes are. Now let's talk about the 7 giant satellites. So bodies that circle the planets, that go around the planets, are called satellites, such as the Earth's moon. Earth's moon is a satellite, so you can also call them moons. It is interesting that the inner planets only have a total of 3 moons. One is the Earth's moon, and Mars has 2 moons, Phobos and Deimos. Mercury and Venus have no moons. However, when it comes to the outer planets, each of them has many, many moons. Okay. So out of the total, all the moons of the planets, we have picked the 7 biggest moons, or the 7 giant satellites. Out of them, the biggest one overall is Ganymede. It is so big that it is bigger than the planet Mercury, actually. So if we look here, the diameter of Ganymede is 5,268 kilometers, whereas the diameter of Mercury is 4,880. So Ganymede, which is a moon of Jupiter, is actually bigger than Mercury. Next in size is Callisto, which is also a moon of Jupiter. So within this are the four Galilean moons. These are the 4 big moons which are most easily seen next to Jupiter, and Galileo was able to identify them quite early on. That's why they are named as Galilean moons, and those are Ganymede, Callisto, Io, and Europa. These all are moons of Jupiter. After Callisto in size, the next one is actually Titan is bigger than Callisto. Titan is a moon of Saturn, and its equatorial diameter is 5,150 kilometers. Then there's Triton, which is a moon of Neptune. There are those masses mentioned, and there are those densities. Substantial atmosphere. There is only one moon which has somewhat of an atmosphere, and that is Titan. Titan is the only satellite in the solar system with a substantial atmosphere. So that is one moon of interest because of having the atmosphere. How do we know that the Titan has an atmosphere? We can see it from the looks. We can talk in a more casual way of how we decide that it has atmosphere, or we can talk in more technical scientific language. Well, if you just look at these, you can see a lot of texture in all these other moons, and that texture is the ground, the solid ground that we are looking at. And so there isn't enough atmosphere to blur that. However, the look of the Titan is very very smooth, and that is because of the atmosphere. Also, we take the light being reflected by Titan and we send it through a spectroscope and make a spectral pattern. And in this spectral pattern, when we find these dips are like the dark absorption lines, which can only be produced by gases. And so there are these distinctive dips. Two of them indicate presence of methane. And then there are dips for hydrogen and oxygen. Those are introduced while coming out from the sun and while coming into the earth. But methane is the one that is produced by Titan. Here's a diagram showing how how these absorption lines are produced. Here is Jupiter's moon Europa. Jupiter's moon Europa is also interesting because it is thought to have an it is supposed to have liquid water, oceans of liquid water under the surface. And by the looks of it, you can see it is covered by frozen water or ice. And underneath that, there is liquid water. So this is an object of interest in terms of finding life, or at least having conditions suitable for life. Again, although by a casual look, we can see that it looks something like there is ice on Europa, but we can test it more scientifically by looking at its spectroscope. And when we see that, we find there are these dips in certain places, which are the same dips that are observed in ice. And that's how we know that this is ice made from water. Let's talk about the belts that can be shown, the characteristic structure of the southern equatorial and northern equatorial belts on the Jupiter. The patterns on Jupiter are made up of white, yellow, and brown colors. And the brown colors typically comes from nitrous oxide. There's also a very characteristic giant red spot, great red spot, which is actually a giant storm that has been raging for more than 300 years. Let's look at Mars. Mars has the red color. It has a very thin atmosphere, and therefore we can see its surface. And that surface is red because of presence of iron oxide. It does have a thin atmosphere. It has polar ice caps. Mars has a tilt, just like Earth's tilt. And because of that tilt, first of all, the poles of Mars do not get as much sunlight. So those are really cold. And so they have ice caps. Plus, because of the tilt, it has seasons. And so alternatively, sometimes the northern polar ice cap disappears. The polar ice caps are actually made up of dry ice or solidified carbon dioxide. So when the northern polar ice cap is facing more directly towards the sun, then it gets more heat and the carbon dioxide sublimates. Sublimation is the process in which a solid directly turns into gas, skipping the liquid phase. So it sublimates and goes over to the southern polar ice cap, and then the reverse happens later on. During this time, there's a lot of carbon dioxide in the air, and there are huge storms. Mars also has the biggest mountain out of all the planets, and that mountain is bigger, taller than the Mount Everest, and it is called Olympus Mons. Let's compare some common properties of the terrestrial and Jovian planets. In terms of distance from the sun, all the terrestrial planets are concentrated within 2 astronomical units, whereas Jovian planets start beyond 5 astronomical units and then go all the way to 30 astronomical units. Terrestrial planets are small in size, Jovian are large. Composition, terrestrial planets mostly rocky materials, iron, oxygen, silicon, magnesium, nickel, and sulfur. Jovian planets made of mostly light elements such as hydrogen and helium. Terrestrial planets have high density, Jovian planets have low density. Now let's talk about some other members of the solar system other than the planets. So there are these other objects which circle around the sun, but they are not big enough for gravity to transform them into a round shape. These are called asteroids. Here's an asteroid, Eros. It is about the same size as the island of Manhattan. Because Eros is so small, its gravity is too weak to have pulled it into a spherical shape. Then there are dwarf planets. As you know, Pluto was categorized, was kicked out of the category of planets and was categorized as a dwarf planet. There are a few definitions. There are a few conditions that an object must satisfy to be called a planet. First of all, it should be big enough for its gravity to make it into a round shape, which Pluto satisfies that one. However, the conditions that Pluto doesn't satisfy are dominating its neighborhood. First of all, Pluto has 4 moons, and one of its moons, Charon, is actually half the diameter of Pluto. So Pluto is not significantly bigger than its moons. So it doesn't quite dominate its neighborhood. Secondly, because of being small and because of having a large orbital period, it hasn't cleared its neighborhood of debris. Plus, after the discovery of Pluto, many other objects were found which were about the same size as Pluto and some even bigger. And so a new category had to be made, and Pluto really fit more neatly into that category of dwarf planets. Here is a listing of some of the main dwarf planets. For example, Eris was found after Pluto, and Eris is actually bigger than Pluto, and yet it's called a dwarf planet. So 7 large trans-Neptunian objects. These are also called trans-Neptunian because these are located beyond the orbit of Neptune. So Quaoar 2003, EL61, Sedna 2005, FY9, Pluto, its moon Charon, and Eris. Another type of member of the solar system are comets. When comets appear, they are the biggest objects that you can see in the sky. And comets are typified by their tail, having a body and a tail. And usually people think that there is one tail, but when we look with very powerful telescopes with very good imaging, we can see there are actually two tails. One is a bluish tail that is made up of gas, and another white tail that is made of dust. The bluish tail actually has ions. Ions are charged particles. And the interesting thing about the tail of comets is that the tail of comets always points away from the sun. The solar wind pushes it away from the direction of the wind, of the sun. Now let's talk about how the craters are evidence of a young or an old surface. So we can see these craters. For example, Moon's surface is very famous for having so many craters. Any medium power binocular or telescope can show us so many craters on the Moon's surface. In the same way, on Earth, there are some huge craters. However, because of the Earth's surface being dynamic and changing, sometimes those are not preserved in its original form. However, sometimes we can notice them when we see them on a large scale from a high altitude. Similarly, there are craters on the Mars. So there's a general rule that a surface that is out of all the planets and moons, a surface that is full of craters is an older surface, and a surface which doesn't have as many craters is a younger surface. That means that the interior of the planet was still molten, and some of the asteroids that hit and created these meteors, some of them punctured the surface and caused the molten lava to come out and fill the craters. And so the surface was reformed, and so it's still young. So when we see that Moon is full of craters, then we can say that the Moon's surface is an old surface, whereas Earth's surface is a young surface. There's also a relationship between the size of the object and whether it is young or old. And this relationship, in a strange way, in an ironic way, is kind of inverse of what you would think. So the bigger objects have a younger surface, and smaller objects have an older surface. How does that work? Well, the reason for that is that all objects, when they started out, they were hot and molten. Now, as a spherical object becomes bigger, its volume increases very fast. As the radius increases, the volume increases as cubed of the radius. However, surface only increases as square of the radius. So a bigger object cannot release that heat so fast. So bigger objects, bigger planets and moons retain the original molten heat for a longer time. And so they are hot and molten for a longer time. And so when they are hit by some very big meteorite, then their surface is punctured and molten lava comes out and resurfaces it, keeping the surface young. Whereas smaller planets and moons like Earth's moon and Mercury, they lose the internal heat very quickly, become solidified on the inside, and after that they cannot resurface the surface. So they have old surface. Earth has a magnetic field. You must have learned that. It is actually produced by the molten interior of the Earth, which has iron in it. Other planets have magnetic fields too, and that is always because of a molten interior which has some kind of a conductive material inside it, either iron or other kinds of ionic salts. Jupiter has a very strong, Jupiter has actually the strongest magnetic field out of all the planets. The sun has super strong magnetic field. Saturn also has a strong magnetic field. Here is a picture of the probe Cassini passing by Jupiter and by Saturn and measuring its magnetism. There is relic magnetism on Mars. There isn't a global magnetism on Mars anymore, like on Earth. On Earth, you can be on any part of the Earth and use a compass, and it will tell you which side is using the magnetic field of the Earth, you can tell which side is the north and which side is the south. But Mars has a very weak magnetic field, and in different places, and it points in different directions. It's a relic magnetism. It is thought that once Mars had a global magnetic field, but as Mars is smaller, it cooled down faster, its interior solidified, and it lost its magnetism, and there's only just some remaining magnetism on the surface. Okay, let's read some more summaries, similarities, and differences between the different planets. Yeah. So comparisons between the inner or terrestrial planets, average distances from the sun, equatorial diameters. We have talked about these, mass, average density. This is all a repeat of what we talked about. Okay, here's some new information about the inner planets. The atmosphere. Obviously, Earth has a very good atmosphere, which has about 70% nitrogen and about 30% oxygen. Mercury has no atmosphere. The presence of atmosphere depends on the mass and gravity of the planet. And so small objects tend to not have atmosphere, whereas bigger objects do have atmosphere. And so that's why Mercury has no atmosphere. Mars has a thin atmosphere. Now, the other similarity is a huge amount of carbon dioxide. The atmosphere being made up mostly of carbon dioxide, and that similarity you can see in Venus and Mars. Both of them, their atmosphere is mostly carbon dioxide with some nitrogen. In the case of Earth, because of the evolution of life and plants, which converted the carbon dioxide into oxygen, we have very less carbon dioxide and we have much more oxygen. The next set of pictures shows the magnetic fields. Out of the inner planets, Earth has the strongest magnetic field. Venus has no magnetic field because it spins very slowly. Spinning is very important for the generation of magnetic field. Mars has no magnetic field, as we described. Mercury has a very weak magnetic field. Then the last set of pictures shows the internal structure. It's almost similar for all the 4 planets, inner planets. There are 3 main parts. The crust, mantle, and core, which the Earth has. Venus has the same crust, mantle, and core, but its core is bigger. What is interesting is Mercury's core is quite big compared to its overall size. Its mantle is quite small and core is quite big. And the core is made up of iron. So much so that sometimes Mercury is called a ball of iron. As you can see, Mars doesn't have much of an iron core, and that is what leads to it having a smaller density. There's a similar diagram that compares the properties of the outer planets, and that analysis has been left for the students to study, and that is an assignment for you to go and look at this similar diagram for Jovian planets, which compares their atmosphere, magnetic field, and internal structure. And with that, we get to the end of this chapter. And please read the key ideas to summarize the main ideas. And with that, this chapter is finished. Thank you.